Importance of binding energy curve. Importance of binding energy curve. Binding energy curve. Importance of binding energy curve. On binding energy curve, binding energy per nucleon for iron 56 is 8.8 mega electron volt, which is maximum. Therefore, iron under bracket Fe56 is most stable. Iron 56, that is Fe56, is most stable nucleus or element, because binding energy per nucleon is maximum, which is 8.8 mega electron volt for iron, or for iron 56 binding energy will be the maximum. Now we can denote a region between element of mass number 40 to the element of mass number 120. This is a region between mass number 40 to 120, and here at this point mass number A is equal to 40, and at that point mass number is 120, and in this region average binding energy will be 8.5 mega electron volt. In this region, all the nuclei or elements have the binding energy per nucleon as 8.5 mega electron volt. Here we have denoted the region in which the average binding energy per nucleon or mass number is 8.5 mega electron volt, and in this region having mass number 40 to mass number 120, all the elements or nuclei are more stable. All the elements are comparatively more stable and non-radioactive. These elements existing in this region having average binding energy per nucleon as 8.5 are comparatively more stable and non-radioactive. More stable and non-radioactive. Now, if we consider uranium 239 or uranium 235, for uranium 239, binding energy per nucleon, average binding energy per nucleon for uranium 239 or 235 is 7.6 mega electron volt or MeV. So for uranium 239, obviously binding energy per nucleon is 7.6 mega electron volt, and we can denote a region in which binding energy per nucleon will be approximately equal to 7.6 mega electron volt, and elements around uranium 239, which is denoted in the diagram, are unstable and radioactive. So this is the region near uranium 239. They have the binding energy per nucleon as 7.6 mega electron volt, and elements existing in this region are unstable and radioactive. On the graph, we can denote the direction along which fission of heavy nuclei having mass number nearer to 40 into smaller nuclei having mass number nearer 60. Similarly, we can denote the direction along which fusion of lighter nuclei occurs into heavy nuclei. This is the direction along which fusion of two or more than two lighter nuclei into a heavy nucleus. Importance of binding energy curve number 1. From the binding energy curve, we can say that the binding energy per nucleon, the binding energy per nucleon, that is B dot E per A or mass number, reaches maximum value of 8.8 mega electron volt, reaches maximum of 8.8 mega electron volt on the curve at the mass number A equal 56. The binding energy per nucleon reaches maximum of 8.8 mega electron volt on the curve at mass number of A56, corresponding to iron 56, corresponding to the nucleus, that is the nucleus of iron, that is the nucleus of iron or iron nucleus under bracket Fe2656. The binding energy per nucleon reaches maximum value of 8.8 mega electron volt on the curve at mass number of 56, corresponding to iron nucleus under bracket Fe2656. Hence, iron nucleus under bracket Fe2656 is most stable nucleus or element. Iron nucleus is most stable nucleus. Binding energy per nucleon reaches maximum of 8.8 mega electron volt on the curve at mass number of A equal 56, corresponding to iron nucleus, that is Fe2656. Hence iron nucleus is most stable nucleus. Iron nucleus is the most stable nucleus. On the curve, binding energy per nucleon for iron 56 is 8.8 mega electron volt, which is the maximum value of binding energy. That is 8.8 mega electron volt is the binding energy per nucleon for iron 56 or Fe56. That's why iron nucleus is most stable nucleus. Iron nucleus is most stable nucleus. Number 2 importance of binding energy curve is the average binding energy. The average binding energy per nucleon is 8.5 mega electron volt. The average binding energy per nucleon is 8.5 is about 8.5 mega electron volt, is about 8.5 mega electron volt for the nuclei having mass number ranging from 40 to 120. Average binding energy per nucleon is about 8.5 mega electron volt for nuclei having mass number ranging from 40 to 120. And these elements like iron 56, these elements like iron 56, krypton 92, barium 141, etc. are comparatively more stable and non-radioactive. These elements like iron 56, krypton 92, barium 141, etc. are comparatively more stable and non-radioactive. The average binding energy per nucleon is about 8.5 mega electron volt for nuclei having mass number ranging from 40 to 120. These elements are comparatively more stable and non-radioactive. That is, iron 56, krypton 92, and barium 141 are more stable and non-radioactive. Now we can denote this region in which elements have mass numbers 40 to 120, and binding energy per nucleon for these elements is about 8.5 mega electron volt, and we have denoted that binding energy range, and these are the position of krypton 92, barium 141. Now this is the region in which elements have mass number ranging from 40 to 120, or near about 40 to 140, 120, and here in this region elements are more stable and non-radioactive. These are the elements having mass number ranging from 40 to 120, or near about 40 to 120, are more stable and non-radioactive. Number 3, importance of binding energy curve. For the elements having high mass number, or for higher mass number elements, for higher mass numbers, the curve reduces slowly. The curve reduces slowly, and for high mass numbers, the curve reduces slowly, and binding energy per nucleon, or binding energy per mass number, for uranium 239, is about 7.6 mega electron volt. The binding energy per nucleon for uranium is about 7.6 mega electron volt. Hence the nuclei having higher mass numbers, nearer to uranium 239, or nearer to any isotope of uranium, are comparatively unstable and radioactive, are comparatively more unstable and radioactive. Of course, it should be radioactive. They should be radioactive elements. So here Fe56, from Fe56, binding energy curve reduces slowly. This curve has downward curvature, or this curve reduces slowly up to uranium 239. And the binding energy per nucleon for uranium 239 is 7.6 mega electron volt. 7.6 mega electron volt. Binding energy per nucleon or per mass number for uranium 239 is 7.6 mega electron volt. And if we denote this region around uranium 239, nuclei or elements will be unstable and radioactive. In this region, elements having mass number nearer to uranium 239 are more unstable and non-radioactive. From this binding energy curve, or from the curve of binding energy, we can say that from the curve of binding energy, we can say that the heavy nuclei nearer to mass number, near mass number A equal to 40, near mass number A equal to 40, the heavy nuclei near mass number 240 are less stable than the nuclei The heavy nuclei near mass number 240 are less stable than the nuclei near mass number A equals 60. This suggests that energy will be released. Energy can be released. Energy can be released if this suggests that energy can be released if heavy nuclei or nucleus, of mass number under bracket A near to 240, that is, energy can be released if heavy nucleus, not heavy nucleus near mass number 240 split apart into smaller nuclei, smaller nuclei having mass number ranging from nearer 60. That is, the energy can be released if heavy nucleus of mass number nearer 240 split apart into small nuclei having mass number nearer to 60. And this process is called nuclear fission. This process is called nuclear fission, in which energy will be released if heavy nucleus of mass number nearer 240 split into smaller nuclei. It is the process that powers atomic bomb. It is the process that powers atomic bombs and nuclear reactor or nuclear power reactions. It is a process that powers atomic bombs and nuclear power reactions. Hence, you can say that heavy nuclei near mass number 240 are less stable than the nuclei near mass number is 60. This suggests that energy can be released if heavy nucleus near mass number 240 split apart into smaller nuclei having mass number nearer 60. This process is called nuclear fission, and it is the process that powers the atomic bomb and nuclear power reactions. Now we can denote the region around mass number 240, and in this region nuclei are unstable and non-radioactive. Nuclei are less stable and non-radioactive, and also you can denote a region around mass number 60 or around iron 56. And in this region around mass number A equals 60, nuclei are more stable and non-radioactive. And in this case, obviously, heavy nucleus having mass number around 240 will split into lighter nuclei along this direction. That means nuclear fission will occur along this direction. That means heavy nucleus having mass number around 240 will split into lighter nuclei having mass number ranging from 40 to 120 or 140. As an example, we can consider the nuclear fission of uranium-235 nucleus. When uranium-239 nucleus is bombarded by thermal neutron, that is slow moving neutrons, thermal neutron will strike the uranium-235 nucleus, and this nucleus will split into barium and krypton, and 3 secondary neutrons will be produced. 3 secondary neutrons, that is fast moving neutrons, will be produced in this nuclear fission reaction. Additionally, large amount of energy will be released in this nuclear fission process. Now we can denote the position of uranium 235 nucleus, barium 141 nucleus, and we can this is the position of krypton 92 nucleus on the binding energy curve. Binding energy curve. This is the direction along which nuclear fission of uranium 235 will occur. This is the direction along which nuclear fission of uranium 235 isotope will occur. Here uranium 235 nucleus, that is heavy nucleus, split into barium 141 and krypton 92 in nuclear fission. And additionally, an energy of 200.4 mega electron volt will be released from this nuclear fission process. Lighter nuclei like hydrogen and helium are less stable. Lighter elements like hydrogen and helium. The lighter elements have nuclei that are less stable than the heavier elements. Up to mass number A equal 60. Up to mass number A equal 60. Thus, two or more than two nuclei or more than two nuclei fuse into a heavy nuclei. Because lighter nuclei are unstable and heavier nuclei are more stable. Two lighter nuclei fuse into heavier nucleus and energy is released. This process is called nuclear fusion. It is the process that powers hydrogen bombs. Again, we can say that lighter elements like hydrogen and helium have nuclei that are less stable than the heavier elements up to mass number A equals 60. That's why two lighter nuclei fuse into heavier nucleus and energy is released. And this process is called nuclear fusion. And it is the process that powers the hydrogen bombs. On the binding energy curve, hydrogen is less stable nucleus. And we can denote the direction along which nuclear fusion will occur. That means two or more than two lighter nuclei will fuse into heavy nucleus along this direction. This is the direction along which nuclear fusion will occur. Nuclear fusion of lighter nuclei will occur into heavy nucleus. Here we are considering the nuclear fusion of deuterium and tritium. This is the position of tritium nucleus on binding energy curve. Deuterium and tritium fuse into helium nucleus. That means two lighter nuclei fuse into heavy nucleus. Deuterium and tritium fuse into helium nucleus, and energy will be released from this nuclear fusion process. Here, deuterium and tritium fuse into helium nucleus and energy is released from this nuclear fusion process.